everybody. We're doing a physics problem on the photoelectric effect. It says calculate the number of photoelectrons per 1.00 millimeter squared area of sodium metal by 500 nanometer EM radiation having an intensity of 1.3 kilowatts per meter squared. That's the intensity of sunlight above the Earth's atmosphere. Given that the binding energy is 2.28 eV, what power is carried away by the electrons, and where does the power go, and how can it be recovered? So when you're doing these kind of problems, you know, if you go to your equation table, or if you remember anything about this section, you want to recall that the change in E, right, equals HF, right? Where H is Planck's constant and F is the frequency. Another way we can, some other information we might want to remember is the frequency is equal to the speed of light over lambda, right? And the lambda actually represents the wavelength, okay? And then in this type of problem, we're probably going to want to think of things like power, right? And power is the number of electrons ejected, right, which we'll denote with N, and E with energy, right? And then, of course, as it mentioned in the problem, BE, right, is the binding energy that we're going to have. So let's go, if you remember too, we have this work equation where it's the kinetic energy of the electron is equal to HF minus the binding energy, right? Now we have all that information, we can start solving the problem. So we're going to start with part A first. It says calculate the number of photoelectrons per 1.00 millimeter squared area by 500 nm. So we're going to start with this equation where the E equals HF. Then we're going to change it to C over lambda equals F. And then so just by that information, we're going to determine that E, right, equals HC over lambda, right? Sorry, my lambda is kind of ugly. And then we could just kind of start filling in information. So we'll set it in as so we're going to use this right here after we manipulated and everything and changed it around and showed the relation of the different equations. We're going to plug in the value for Planck's constant, which you can get from a table or you can look it up online. Joules times seconds, right? Times the speed of light, which is 3.00 times 10 to the 8th meters per second. And then we're going to do all of that over the information we got for lambda in here in the problem. But we're going to have to, convert it a little bit or write it in scientific notation. Now, if we plug all that into the calculator, we're going to go fraction 6.626. Right? And then we're going to get an answer of 3.976 times 10 to the negative 19 joules. Okay, that was just for part A. So not that much energy. As you can see, it's a very small amount, but still quite a bit. So now we're going to solve for more information, because it was asking calculate the total number of photoelectrons. So we're going to need to solve for n also. We can also plug in some information that we had. Right? And then that's information. This information we got here for n is from the given information of the intensity of the sunlight above the atmosphere. And then we're going to take this value for E that we got, right? And we're going to plug it in to the bottom right here. And since we want the answer in seconds, we're going to have to do like a unit conversion. Okay, and then let me plug this into the calculator. It's, what did we say it was? It was 1.3 times 10 to the third over 3.976 times 10 to the negative 19, right? But then we want to convert it to seconds, so we take that answer times 1 over 1. Times, what did I make a mistake? Times, yes, I think you had to square this. Oh. Okay. So, if we take that information, we're going to get 3.272 times 10, what did I say, 21 seconds times meters squared. But we need to further change that to, what did I type in the calculator? Okay. And then let me re-plug all this back into the calculator. You're going to get a lot of seconds. So when we do this and do the appropriate like unit conversions and everything, you're going to get 3.272 times 10 to the 9th seconds. That's a long time. Okay, so for part B, it was asking us that given that the binding energy is 2.28 eV, what is the power carried away by the electrons? So I guess we're talking about the relation between the electrons. So we'll say that the relation between n is the number of photons emitted per second, or photon emission, and power is emitted per second, and power is kinetic energy, right? So we could do the relation as power equals n times the kinetic energy of the electron. So if we just trying to get, power, right, we're using n for the seconds, right? And then joules. Just make sure I put that in right. We're going to get watts. That's, as you can see, that's not a whole lot of power. We got this value from a table. But yeah, so to answer the question, the last part, it says, where does the power go and can it be recovered? Well, I guess some of the energy goes to the sodium metal to free the electrons, which I guess that would be the binding energy. And I guess the only way the power could be recovered is by absorption that would have to occur like spontaneously. So I guess the energy released is the 2.28 eV. And that's it for this problem.